Our first example of macroscopic balances involves the use of the mass and momentum balances to calculate the force on a reducing bend. In this example, water at 20 degrees Celsius flows steadily through a reducing pipe bend as shown in the figure below. Known conditions are the pressure at position 1, which is up here, is 350 kilopascals. The pipe diameter at position 1 is 25 centimeters, and the mean velocity of the turbulent flow at position 1 is 2.2 meters per second. At location 2, which is down below here in the figure, the pressure is 120 kilopascals, and the diameter of the pipe is 8 centimeters. The air pressure is assumed to be 100 kilopascals. Neglecting the bend and water weight, estimate the total force which must be resisted by the flange bolts. So in this example, we have a long pipe coming here from left to right, and another smaller pipe from right to left down below here. And these are connected by this bend. It's called the reducing bend because the diameter goes from larger on the top to smaller below as this thing goes around a 180-degree turn. Now the flange bolts connect the flanges of the pipes. The flanges are the little things that protrude out from the pipe walls where we join two segments of pipe together, and the bolts are clamped over them to hold the pieces of pipe together. So we can look at the detailed notes for force on a reducing bend, as shown here. We've drawn the sketch of the system, and we have the known and unknown quantities. So we know the density of water is 1,000 kilograms per cubic meter. We know the pressure, velocity, and diameter at position 1, and we know the pressure and diameter at position 2. We don't know the velocity at position 2. It's also convenient to draw a coordinate system, so I've shown x going to the right and y going up. Consequently, we can see the velocity vector u1 is in the positive x direction, and velocity vector u2 is in the minus x direction. We'll return to this later, but understanding how the velocity can be written in vector form is very important when writing the momentum balance. We're assuming that the flow is at steady state, the density is constant, and there's turbulent flow such that the velocity is nearly uniform over the cross-section of the pipe. Therefore, when we refer to velocity u1 or u2, that's simply the average velocity of the fluid across the pipe cross-section at that location. We're asked to neglect the weight of the water in this bend because we don't know the details of the geometry, and therefore we don't know how much water is included in here, and so we can't actually compute the gravitational force on this. Moreover, the weight of gravity would have a downward force on this, which would create a torque on these bolts that complicates the problem beyond what we need to deal with here. So a simple analysis shows that there are two primary contributions to the force that the flange bolts must resist. First, there's a pressure in the water in the top pipe here, and also in the bottom pipe below. So this pressure tries to push the bolts apart, tries to separate the pipes. So that's the first force that we're going to have to compute. Secondly, there's a change in the momentum of the water as it moves around the bend. On the top, at position 1, the water is moving in the plus x direction. Down below, the water is moving in the minus x direction. So that change in direction requires a change in the momentum, and the change in momentum requires a force to be applied to the fluid in order to affect the momentum change. That force is supplied by this right-hand side of the bend. So the second force that tries to push these bolts apart arises from the force on the pipe necessary to create the change in momentum to redirect the water from left to right to left, or from the plus x to the minus direction. So we expect those two contributions, the pressure and the change in momentum, to contribute when we look at the momentum balance. Now if we look at the momentum balance in the simplified macroscopic balances, for example, We need to know density, cross-sectional areas, which we know, pressure at 1 and 2, which we know. The force, FSF, is the thing we want to actually compute. We're told to neglect the weight of the water, so we can neglect this m total g term. So the only thing we don't know is the mean velocity at position 2 in the system. So before we can apply the macroscopic momentum balance, we would have to use the macroscopic mass balance to relate the velocity at position 2 to the velocity at position 1 and the cross-sectional area of the tubes at those two locations. So we're going to go through this analysis first using the detailed integral equations. It's rather tedious to simplify them, but it's good to go through once just to understand how to do it. And then after that, we'll return to the problem using the simplified balances just shown, which can get the same answer much more quickly with a lot less effort. So, proceeding forward, first thing we note is that velocity u1 is going to be regular u1 scalar times ex, and the velocity vector u2 is minus u2 ex, just because velocity 1 is in the plus x direction, and velocity at point 2 is in the minus x direction. We already discussed this, but it's good to note when we apply the momentum balance. The next thing we need to do is draw a control volume. So when you're drawing a control volume for the system, you want the control volume to enclose the parts of the system that we do not know much about. So in this case, we don't know the details of the geometry of the bend, we don't know the fluid flow, what's actually going on in there. So we want the control volume to enclose the parts of the system we're ignorant about, because we don't have to know those details. And we want the surface of the control volume to intersect the system where we know something about the flow. So for example, at position 1 up here, the velocity is uniform and towards the right in the plus x direction. Down below, at position 2, the velocity is essentially uniform and in the minus x direction. So it's a good idea to have the control volume surface pass through those points where we know the velocity and the pressure in the system. If the control volume intersected somewhere along this bend, we don't know the details of the flow, nor do we know the details of the pressure, and so it's going to be impossible to evaluate the surface integrals when we're computing pressure forces or rates of momentum coming in and out of the system. So you want the control volume to intersect your system where you know something about the velocity and hopefully something about the pressure. Moreover, if you're trying to compute the force that a solid exerts on the fluid, you also want your control volume to intersect your system at that location. So for example, in this case, the flange bolts are where the solid force is applied to the system to keep these things together. That's the FSF we want to compute. So we want our control volume surface to pass through the flange bolts, because therefore the solid fluid interface now corresponds to the surface of the control volume, and it can therefore be computed. Once we draw the control volume, anywhere you have an inlet or outlet, you need to figure out what the outward unit normal vectors are relative to the control volume surface. So at position 1, we can draw unit vector n1. It points to the left in the minus x direction. At position 2, the outward normal also points to the left. Therefore, n1 and n2 are both equal to minus the ex unit vector. Note that the normal vector is not necessarily in the direction of flow. At position 1, the flow is in the plus x direction from left to right, but the normal vector points outward from the control surface, and therefore it points to the left, and consequently it's the same at both positions 1 and position 2. We don't have to worry about the normal vector on the other sides of the control volume because there's no flow passing into or out of the system at those locations. And so we only need to worry about the normal unit vectors where there's flow or fluid entering or exiting the system. So the next step is to apply the integral mass balance to figure out what the velocity at position 2 is. So we write the integral mass balance. It's the time derivative of the total mass in the system. That's the integral of the density over the volume. And that's equal to minus n dot u minus vs rho ds. This is, on the right hand side, the net rate that mass flows into the system. The next step is to simplify each of the terms in these integral expressions and then proceed to evaluate. So our system is assumed to be at steady state, so the time derivative vanishes. Left-hand side is simply 0. On the right-hand side, our control surface is not moving. Therefore, Vs, the velocity of the control surface, is simply equal to 0. So we simply have that 0 is equal to the integral of n dot u rho ds over all the surfaces where fluid crosses or enters or exits the system. So what we now do is we take this surface integral and we split it up into one integral for each entry or exit point into the system. So left hand side is 0, right hand side is minus n1.u1 rho ds integrated over surface S1. That's the surface on the top where we have the wide pipe. And then we have minus the integral over S2, that's the surface on the bottom where we have the narrow pipe, n2.u2 rho ds. So we simply substitute n1 and u1 on surface S1 and n2 and u2 on surface S2 when we're evaluating this surface integral. So now the next step is simply to substitute. n1 is minus the ex unit vector. u1 is simply u1 scalar times ex. So if we do that dot product, the integrand here becomes minus the u1, which is a scalar quantity, rho, integrated over the surface S1. The second term is minus. Now n2 is also equal to minus ex, the x unit vector, and u2 is equal to minus the scalar u2 times ex, because the velocity at point 2 is flowing in the minus x direction. So therefore, if we evaluate this dot product, minus ex dotted with minus u2 ex gives us plus u2. So proceeding further, we see that the integral, if we look at the sign of the first one, we have a minus u1, so that becomes positive. And the second term is a minus a positive integral. So we bring this second integral to the left-hand side of the equation, and therefore we see that the integral of u1 over surface 1 is equal to the integral of u2 over surface 2. And we've canceled out the density because the density is constant. So since the velocity is uniform across or over the cross-sectional areas of the pipes, the integral of the velocity over the cross-sectional area is simply the product of the cross-sectional area and the velocity. So the integral of u1 ds over S1 becomes u1 times S1. S1 is surface area, the cross-sectional area at position 1. And that's just equal to u2 times the cross-sectional area at position 2. Since it's a circular pipe, we can simply substitute this here. u1 times S1, S1 is pi d1 squared over 4, is equal to u2 times S2, S2 is pi d2 squared over 4. Solving for u2, we see that it's equal to d1 over d2 squared times u1. Substituting in numerical values, it's 25 centimeters divided by 8 centimeters quantity squared times 2.2 meters per second gives us that the velocity at position 2 is the very large 21.48 meters per second. So because the pipe cross-sectional area or the pipe diameter has been reduced so significantly, the velocity has to increase quite a bit in order to preserve a constant mass flow rate in the steady state system with constant density. So we can see the velocity at position 2 is almost 10 times larger than the velocity at position 1. With u2 now computed, we know the velocity and pressure at both positions 1 and 2, where we have inlets and outlets into the system, and so we can then proceed to the integral momentum balance to actually solve for the force that the flange bolts exert on the system. And as I mentioned previously, the FSF, the force of the solid on the fluid, is transmitted through contact between the solid and fluid. That's where the flange bolts are. And so, as I said before, we want the control volume to intersect the locations where the force is to be computed. The control volume that we've already drawn that passes through the flange bolts satisfies this constraint. and therefore allows us to properly compute the force that we want from the momentum balance. As a further note, before we proceed to the momentum balance, we note that air pressure exerts a force on all sides of the control volume except where the fluid is entering or exiting the system. So for example, if we look at this schematic diagram here, on this right-hand side of the control volume, we have air pressure exerting a force. On the left-hand side of the control volume, air pressure will also exert the same force, and so these two will cancel. Similarly, air pressure will exert a force on the top of the control volume, and it will also exert a force on the bottom of the control volume. But because it's just constant pressure on both sides of the control volume, these forces cancel. Difficulty occurs when we look at the inlets and outlets. If we look right here, we look at position 1 over the cross-sectional area of the top pipe. The pressure here is 350 kilopascals. That's the pressure of water. If we go to the right-hand side of the control volume, we take the projection of this cross-sectional area of the pipe on the right-hand side of the control volume, the force of pressure on this side is going to be air pressure. And there's no air pressure to balance it because we have the water pressure on the opposite side. Similar situation happens down below at position 2. We have water pressure down here, it's 120 kilopascals, but in the projection of this on the right-hand side of the control volume, it's air pressure, and therefore there's an imbalance. So wherever you do not have an inlet or outlet, the air pressure force is simply going to cancel and can be ignored. When you have inlets and outlets, however, you have to worry about the effects of air pressure on the opposite side of the control volume that's equal to the projected area of the cross-sectional area of the pipes where we have flow going in and out. So this can be annoying to keep track of. And a simple way to remove this problem is to use the gauge pressure. So the gauge pressure is simply the pressure minus atmospheric pressure. This is comparable to setting atmospheric pressure equal to 0. So if you use the gauge pressure to compute the pressure force at position 1 in the top pipe, and the gauge pressure to compute the pressure force at position 2 in the bottom pipe, you don't have to worry about the unbalanced air pressure on the right-hand side of the control volume, because in terms of gauge pressure, the air pressure is now 0. And so when you use gauge pressure, you don't have to worry about the force due to air pressure anywhere in the control volume. All you have to do is use gauge pressure when you're computing the pressure force on any inlet or outlet into the system. That makes things much easier and prevents a lot of confusion. So consequently, the take-home point is whenever you're applying the macroscopic momentum balance, you want to use gauge pressure for all the pressure terms in the equation. Once again, gauge pressure PG is equal to the regular thermodynamic pressure minus atmospheric pressure, whatever that may be. So with this caveat noted, we can proceed to the integral momentum balance as written here. So we have the rate of change of the total amount of momentum in the system is equal to the net rate momentum comes into the control volume due to fluid flow in the inlets and outlets, plus the effects of gravity, the force of gravity on the control volume, plus the stress integrated over the cross-sectional area for every inlet or outlet. So this is the force exerted by the fluid outside the control volume at any inlet and outlet, plus the FSF, the force of the solid in the fluid. This is what we want to determine. This is the force that the flange volts exert on our system. So, next thing, we just simplify this equation just like we did for the macroscopic mass balance. We're at steady state, so the time derivative term is equal to 0. It's a vector equation, so we keep it with a 0 with an underline. We look at the flow term. Well, the control volume is stationary, so Vs, the surface velocity, is equal to 0. Next term, we're told to neglect the weight of water and the bend in the system, so we can neglect the body force term here. We don't really know the details of the geometry either, so it will be impossible to actually compute this. So this term is negligible. Moreover, we don't know the details of the velocity field, and therefore we cannot compute the viscous stresses, and so the approximation we make is that the viscous stress tensor tau is essentially equal to 0. So we're ignoring viscous stresses in the inlets and outlets. And this is always a good first approximation for any of these macroscopic flow problems. Consequently, this integral over the surface of the stress simply reduces to an integral of the pressure in the fluid at every inlet and outlet in the system. So with these simplifications, the next step is simply to substitute for the unit normal vector n and the velocity u over the inlets and outlets. And we can rewrite this surface integral over S in terms of the sum of integrals over S1 and S2. And if we had more inlets and outlets, we would add those in as well, just as we did for the mass balance. So, proceeding with these substitutions, we find that 0, we were at steady state, is equal to minus. Now we wrote these surface integrals, we broke them up into the two surfaces, the inlet and outlet. We have an integral over S1, n1.u1 rho u1 ds. Then we have the integral over S2 of n2.u2 rho u2 ds. So those are simply the flow terms written out for the inlet S1 and the outlet S2. Next step, we substitute. N1 is minus EX. U1 vector is U1 scalar times plus EX. And similarly here. So when we do the dot product of minus EX with EX, we get minus 1. And so this integrand becomes minus rho U1 scalar squared times EX. And we retain the minus sign out in front. Do the same thing for the surface 2. Normal vector N2 is minus EX. U2 vector is minus U2 scalar EX because the flow is in the minus X direction at position 2. And then similarly for the second U2 term. So when we have a minus minus minus, we get one minus sign, rho U2 squared times EX integrated over surface S2. Proceed similarly with the pressure terms, but we use gauge pressure. So we rewrite the integral over S as two integrals over S1 and S2, preserving the minus sign out in front of the integrals as we had in the previous equation. We have P1 gauge times N1. N1 is minus EX, so this becomes positive. And then we have P2 gauge times N2. N2 is minus EX, so that term also becomes positive. And then we have finally the FSF, the solid fluid interaction force that we want to solve for. So, keeping this here and bringing the other four terms to the left-hand side, we find that FSF is equal to minus the integral over S1, rho U1 squared ds, minus the integral over S2, rho U2 squared ds, minus the integral over S1, pressure 1 gauge ds, and minus the integral over S2, pressure 2 gauge ds, all times the x unit vector. There's no y component in this equation, so we can simply take the x component of the equation by dotting everything with the x unit vector, and we find that FSF in the x direction is simply equal to minus the integral over surface 1 of rho u1 squared plus p1 gauge, minus the integral over surface 2, rho u2 squared plus p2 gauge. Because the velocities u1 and u2 and the pressure are assumed to be uniform over the cross-section of the tube, the integrals are simply the product of the cross-sectional area and the integrands. Consequently, the force of the solid on the fluid is equal to minus the cross-sectional area at surface 1 pi over 4 d1 squared times the integrand, rho u1 squared plus, and p1 gauge I've written as p1 minus p atmosphere. And we have minus S2 pi over 4 d2 squared times rho u2 squared plus P2 gauge, and P2 gauge is P2 minus P atmosphere. We can then substitute numerical values. V1 is 0.25 meters or 25 centimeters. Density is 1,000 kilograms per meters cubed. U1 is 2.2 meters per second. Pressure 1 is 350,000 pascals, and atmospheric pressure is 100,000 pascals. For position 2, the diameter is 0.08 meters or 8 centimeters. You want to keep these all in consistent SI units. Density is 1,000 kilograms per cubic meter. The velocity is the very large 21.48 meters per second. Pressure is 120,000 pascals, and an atmospheric pressure is 100,000 pascals. So when we put this together, we get two terms. The first is minus 12,509 newtons, and the second is minus 2,419 newtons. So putting this all together, we find that the total force the flange bolts must resist is minus 14,929 newtons. There's a minus sign indicating that the bolts have to exert a force in the minus x direction, and that's because the pressure and the change in momentum both exert forces in the plus x direction. They try to blow off the bend in the plus x direction towards the right, and as a result, the bolts have to exert a force to the left to prevent the bend from flying off in the x direction. So that hopefully is a straightforward application of the integral balances for this problem. Next, I want to briefly go over how we can use the simplified macroscopic balances to get the same result with a lot less effort. So, if we look at the simplified macroscopic balance handout, mass balance says that the volumetric flow rate at position 1 is equal to the volumetric flow rate at position 2 at steady state. And the momentum balance is written as shown here, where L1 is a unit vector in the direction of U1, and L2 is a unit vector in the direction of U2. So, we return to our notes, go to the next page, say, okay, first step, let's use the macroscopic mass balance at steady state simplified form. So the volumetric flow rate at 1 is equal to the volumetric flow rate at 2. That tells us that rho U1 S1 is equal to rho U2 S2. Densities cancel. U2 is S1 over S2 times U1, which is D1 over D2 squared U1, and we get the same 21.48 meters per second that we found by using the integral mass balance. The momentum balance is where the simplifications really appear. So we write out the momentum balance from the handout in the simplified macroscopic balances. So 0 at steady state is equal to rho U1 squared S1 times unit vector L1 minus rho U2 squared S2 times unit vector L2, plus we still use gauge pressure, so P1 gauge S1 L1 minus P2 gauge S2 L2, plus the force of the solid in the fluid, which is a term that we want to solve for, and then plus the total mass times gravity, which is the gravitational force, and this is what we're told to neglect, so we ignore that term. So all we have to do here is identify the unit vectors L1 and L2, and then substitute values, and we can solve directly for FSF. So I have a little sketch here of the system. Here's our big bend on top and a little one down below. So L1 is a unit vector that points in the direction of velocity U1. Velocity U1 is from left to right in the plus x direction because flow is entering the system, and so L1 is equal to the EX unit vector. Conversely, down below, the flow is from right to left in the minus x direction because flow is exiting the system. So the unit vector L2 that points in the direction of U2 is equal to minus EX. Notice that L1 and L2 are not the same as the unit normal vectors that we drew when we used the integral form of the control volume analysis previously, because the normal vector n always points away from the control volume, whereas the unit vector L1 and L2 always point in the same direction as the velocity at that point in the system. And so L1 and L2 are in general different than N1 and N2. Aside from that distinction, this is a very straightforward application. So we can solve this equation for FSF, the force the flange bolts exert, and we find this equal to minus rho U1 squared plus P1 gauge S1 times L1 plus rho U2 squared plus P2 gauge S2 times L2. L1 is plus EX, as we've just said. L2 is minus EX. And so we get two terms here. We get minus pi over 4 D1 squared times rho U1 squared plus P1 gauge EX, and minus the same thing evaluated at location 2. So this is exactly the same result that we found from using the detailed integral analysis above, but we've done it with only a couple minutes of effort. So I strongly encourage you to become familiar with the simplified form of the macroscopic mass and momentum balances and how to apply them, since this will greatly facilitate your ability to solve homework and exam problems involving macroscopic balances. Being able to use the integral equations is good in general, but for the problems we're going to focus on, the simplified mass and momentum balances in the handout are sufficient, and therefore they should be studied until you're comfortable with the application. The main challenge is just understanding what is meant by L1 and L2 and not confusing the signs. Otherwise, the application is entirely straightforward, and it can result in rapid solution of a number of interesting engineering problems.